What if the most important spacecraft in human history is the one nobody talks about? What if it just did something so strange that scientists still cannot fully explain it? Before we go any further, if you want to see where this story leads, tap that like button right now, hit subscribe, and send this video to one person who loves space as much as you do. It genuinely helps this channel keep making videos like this one. Now let's get into it. Right now, two machines are moving through the darkness beyond our solar system. Everybody knows the famous one. Voyager 1, the record breaker. The spacecraft that carries a golden disk with sounds and images of Earth, meant to speak for our entire species if it is ever found by someone or something out there. Voyager 1 is the one that left the protective bubble around our sun back in 2012 and has been quietly making history ever since. It shows up in headlines, it gets the documentaries. It gets called the farthest human-made object ever built, and that title is completely true. But there is a second machine out there. Quieter, less famous, moving in a completely different direction through a completely different patch of space over 13 billion miles from Earth. And here is the twist almost nobody knows. This second spacecraft, Voyager 2, carried something into interstellar space that Voyager 1 lost decades before it even got close to the edge. A single working instrument, one that turned out to be the key to understanding the true boundary of our solar system. And what that instrument measured did not simply back up what Voyager 1 had already found years earlier, it challenged it. It complicated the picture. It forced scientists to admit, in plain words, that some of their long-standing models were simply wrong, because Voyager 1 was flying blind at the exact moment it mattered most. Voyager 2 was not. And right now, in 2026, Voyager 2 is at the center of one of the riskiest operations NASA has ever attempted on any spacecraft. Engineers gave it a nickname that sounds almost like a joke, except nothing about it is funny. They call it the Big Bang. A total, all-at-once rewiring of the spacecraft's remaining power system, carried out across a distance so vast that a single command takes over 16 hours just to arrive. And the answer takes another 16 hours to come back. There is no do-over. There is no backup plan sitting in a warehouse somewhere. If it goes wrong forever, and there is nobody who can fly out there to fix it. And what happens to Voyager 1 later this year depends entirely on whether Voyager 2 survives what is happening right now. Let's start at the beginning, because the story of how we got here is almost as strange as the discovery itself. Voyager 2 lifted off from Earth on August 20th, 1977, 16 days before its twin, Voyager 1. Yes, you heard that right. Voyager 2 actually launched first. The numbering has nothing to do with launch order. It has to do with which spacecraft was expected to arrive at its destinations first. Voyager 1 was placed on a faster, more direct path toward Jupiter and Saturn. Voyager 2 was sent on a longer, far more complicated journey. And that longer journey gave it the chance to do something no spacecraft before it, and no spacecraft since has ever managed. Voyager 2 is the only spacecraft in human history to visit all 4 giant planets in our solar system: Jupiter, Saturn, Uranus, Neptune. Every single outer world seen up close, one after another, using a rare planetary alignment that only lines up once every 176 years. Mission planners in the 1960s realized this alignment was coming and understood that a single spacecraft, using the gravity of each planet to slingshot toward the next, could visit all 4 in one continuous journey. Miss this window, and nobody alive today would see it happen again. Voyager 1 took a different path. It skipped Uranus and Neptune entirely, took a closer shortcut past Saturn's largest moon, Titan, and aimed straight out of the solar system, toward interstellar space. 2 spacecraft, 2 very different assignments, 2 very different pictures of what the outer solar system actually looks like. But that decision came with a real cost, and the cost was time. Voyager 2's longer, more complicated route meant it reached the true edge of the solar system. The boundary scientists call the heliopause, years later than its twin. Voyager 1 crossed that boundary in August 2012. Voyager 2 did not cross until November 2018, over 6 years later. 6 years in which Voyager 1 sat alone out there in interstellar space, sending back readings that puzzled scientists deeply, but readings that carried a massive hidden gap. Here's the detail almost nobody brings up when they talk about Voyager 1's famous crossing: its plasma instrument, the device built to directly measure the temperature. Density and speed of the charged particles surrounding it had already stopped working. Not at the boundary. Not once it reached interstellar space. It failed years earlier before the spacecraft had even passed Jupiter on its outbound journey. Decades before Voyager 1 ever reached the true edge of the solar system. The one tool that could have told scientists exactly what that edge looks like from the inside had already gone completely silent. So when Voyager 1 made history in 2012, crossing into interstellar space for the first time ever, it did it with a blind spot at the center of the story. Scientists could estimate what was happening using other instruments, cosmic ray counters, magnetic field readers, radio wave detectors, but they could not directly measure the plasma itself. On either side of that boundary, they were working around a gap in the data that had existed for over 3 decades, and there was nothing anyone could do to fill it after the fact. Voyager 2's plasma instrument, though, was still alive, still working, still sending clean, direct readings home across billions of miles. And when Voyager 2 finally crossed into interstellar space in November 2018, it did something Voyager 1 physically could not. It measured the plasma directly on both sides of the boundary at the exact moment of crossing. For the first time in the history of space exploration, humanity had a real, direct reading of what interstellar space actually feels like, taken by a machine physically sitting inside it. The results came out in late 2019, published together across 5 separate scientific papers, and what those papers described did not simply confirm the old picture built from Voyager 1's data. It rewrote large parts of it completely. The first shock was about the shape of the boundary itself. Scientists had always pictured the heliopause as a thin, sharp line, a clean edge where the outgoing solar wind stops and interstellar space begins, almost like a wall separating 2 rooms. The best models placed this transition zone at a few 100,000 miles wide at most. What Voyager 2 actually found was a wide, blurred zone, stretching roughly 100 million miles, sitting just outside the boundary, in territory that was supposed to be pure interstellar space from the very first step. Instead, there were fingers of interstellar material reaching inward, pressing into the edge of the solar system like roots slowly growing into cracked stone. Voyager 1 had hinted at something similar on its own approach years earlier, but what it saw was different in character. It found a region where the outgoing solar wind had slowed to almost nothing, like waves finally running out of energy just before they reach the shore. Voyager 2, crossing at a completely different point on the opposite side of the solar system, found a thinner layer with entirely different plasma behavior. Same boundary. 2 separate crossings, 6 years apart, and 2 structurally different stories. One of the lead scientists on the mission put it plainly, and the honesty in that statement is worth sitting with. Both spacecraft crossed the heliopause at almost the exact same distance from the Sun, even though one crossing happened while the Sun was near its most active period, and the other happened while the Sun was calm and quiet. According to every existing model at the time, that boundary should have shifted noticeably, depending on how much energy the Sun was pushing outward. Instead, it barely moved at all. And the honest answer from the scientists who study this for a living, people who have spent entire careers on this exact question, was simple. We do not know why. Now let's talk about temperature, because this is where things get even stranger. The plasma carried outward by the Sun is scorching hot, not in the way we feel heat day to day, but in the sense that its particles move at extraordinary speed, which is exactly how temperature is defined in this kind of physics. Scientists expected a dramatic temperature swing right at the boundary, a sharp line where hot solar plasma meets the much colder plasma of deep space. Voyager 2 confirmed that the drop was real, and even sharper than predicted. But the true surprise came from what sat on the other side of that line. For the first time ever, Voyager 2's still-functioning instrument measured the actual temperature of interstellar plasma directly, rather than estimating it through theory, somewhere between 30,000 and 50,000 degrees. That sounds unbelievably hot by everyday standards, but compared to the tens of millions of degrees, measured just inside the boundary, it is genuinely cold in comparison. And here is the part that really matters. Before this measurement, scientists had only been able to guess at that number using calculations built on assumptions. The actual number, measured directly for the first time in history, turned out to be roughly half of what earlier estimates predicted. An entire generation of models had quietly been built on a number that was wrong by a factor of 2, and nobody knew it until Voyager 2 crossed that line with a working instrument. Then came the third discovery, the one that changed how scientists talk about the boundary. The edge of our solar system leaks, not in a poetic sense, literally. Particles cross that boundary in both directions, constantly, quietly, all the time. Voyager 1, coming in from one direction, detected interstellar particles pushing their way inward, slipping into the solar system from outside like water seeping under a door. Voyager 2, approaching from a completely different angle years later, found the opposite pattern happening on its own side. A steady trickle of particles from inside the solar system, leaking outward into interstellar space before the spacecraft had even technically crossed the boundary line. 2 spacecraft, 2 different locations, 2 different mechanisms driving the leak, but the same underlying truth sitting underneath both discoveries. The heliopause is not a wall. It behaves far more like a coastline, where the tide moves in both directions at once, constantly mixing water from 2 different oceans that were never as separate as we assumed. One of the most senior scientists on the mission described it exactly that way, and the description stuck with researchers for a reason. The Voyager probes are not really showing us where the Sun ends. They're showing us how the sun continues to interact with everything that lies beyond it. There is one more number worth sitting with before we move on, because it puts everything else in perspective. For decades, most people assumed the space between stars must be close to empty. A near vacuum, thin and quiet, almost nothing at all. Both spacecraft, measuring independently from two different locations, found the opposite. The plasma, sitting just outside the heliopause, is roughly 40 times denser than the solar wind found right at the boundary itself. Interstellar space is not empty. It is a quiet, cold, but genuinely substantial ocean of material, and our entire solar system behaves like a warm bubble pressed into the edge of it. Now stay with me, because this is where the story becomes something more than just numbers on a page. Thanks for sticking with this so far, because we are only about halfway through the real story. If this is blowing your mind even a little, do me a favor and drop a comment telling me which discovery surprised you the most. It genuinely helps this video reach more people who would love this kind of story, and I promise I read every single one. Step back for a second and think about what Voyager 2 actually represents here, because this entire situation, one spacecraft losing its most important instrument decades early, the other one somehow keeping its version alive against impossible odds, was not something engineers could have fully planned for back in the 1970s. But the two spacecraft mission itself was absolutely intentional, and understanding why matters. The people who designed this mission, working with computers far weaker than the phone in your pocket, understood something simple but powerful. One spacecraft alone can never tell you whether what it finds is normal or a strange exception. You need two different directions, two different timings. Only with two data points can you actually start building a real picture of what the edge of the solar system truly looks like. Rather than assuming one measurement tells the whole story, what nobody could have predicted was which spacecraft would end up carrying the instrument. That mattered most when it finally counted. Voyager 2's plasma sensor, still working after more than 4 decades, bathed in the harsh radiation of deep space, ended up filling a gap in human knowledge that had existed since 1980. Nobody designed it that way on purpose. It simply happened to work out that way, and it changed everything scientists thought they understood about the true edge of our cosmic home. Now, here is what is actually happening this very summer in 2026, and why it matters so much more than most people realize. Voyager 2 currently has 3 working science instruments left on board. The plasma sensor that made the historic 2018 crossing measurements possible, a working magnetometer, still tracking the magnetic field around it, and a working plasma wave detector, still listening to the electrical hum of the space it travels through. Together, these 3 instruments are doing something nothing else in the entire history of astronomy has ever done, providing a live, ongoing direct measurement of interstellar space from a machine that is physically sitting inside it, moving at over 34,000 miles an hour, far beyond anything we could send a replacement for anytime soon. But there is a countdown running quietly in the background, and it cannot be stopped, paused, or reversed. Each spacecraft is powered by a slowly decaying radioactive source, a small block of plutonium sealed inside a generator back in 1977. Every single year, that power source loses roughly 4 watts of usable energy. It is a fixed, unavoidable law of physics, ticking away no matter what anyone on Earth decides to do about it. Voyager 2 currently has slightly more power remaining than Voyager 1, which is exactly why it still has 3 working instruments, while its twin recently had to permanently shut one down earlier this year, just to stay warm enough to keep functioning at all. That is where the Big Bang comes in. The plan, as described by the small engineering team responsible for both spacecraft, is to completely restructure how power flows through the machine, turn some systems off entirely, swap other components over to lower power alternatives, all in one single, coordinated, simultaneous move, instead of one careful, tested step at a time, the way engineers would normally prefer to operate. And the reason for doing it all at once, rather than slowly and safely, is actually about avoiding an even bigger and more immediate danger. During any power system change, there is a brief moment where the spacecraft sits caught between its old setup and its new one. That in-between moment is genuinely dangerous, because Voyager's built-in safety systems are designed to automatically start shutting components down. The instant they detect the power draw, slipping even slightly out of balance, the longer a spacecraft lingers inside that unstable in-between state, the higher the risk that its own automated safety protocols trigger an emergency shutdown that nobody on Earth asked for, and nobody on Earth can undo from 13 billion miles away, 16 hours after the fact. So the engineers made a deliberate choice to favor speed over caution. Get through the dangerous middle stretch as fast as physically possible, even if that means changing everything at once instead of one careful piece at a time. If the plan works, Voyager 2 could gain at least another full year of usable science time, possibly more. And if it works successfully on Voyager 2 first, the exact same nerve-wracking procedure will be attempted on Voyager 1, with hope that a similar fix might even help bring back the instrument it recently had to shut down. Every single command sent during these tests takes over 16 hours to arrive at the spacecraft. Every response it sends back takes another 16 hours to return to Earth. A basic yes or no answer to one single engineering question costs an entire day, just in travel time for light itself, moving as fast as anything in the universe can possibly move. And the team running this operation is small, tightly knit, and increasingly rare. Many of the original engineers who designed and built these spacecraft have long since retired or passed away. The people running the mission today had to learn old systems, old programming languages, and design philosophies from an era before their own careers even began, just to keep speaking to machines that were built before the internet existed in any form we would recognize today. This is not just a technical challenge sitting in a lab somewhere. It is a genuine race against time, run by a small group of dedicated people holding on to specialized knowledge that cannot simply be looked up in a modern textbook. Think about what that actually means in practice. Before this procedure can even be attempted, every command has to be written, checked, and rechecked, because there is no way to pause halfway through and ask the spacecraft what it is currently doing. By the time a status update comes back confirming the last step worked, 16 hours have already passed and the team is committed to whatever happens next. It is a bit like performing surgery through a mirror in slow motion on a patient you cannot see or touch, where every single instruction has to be correct on the first try, because there's no way to react in real time if something starts to go wrong. If you are the kind of person who actually wants to understand how this ends and not just scroll past a headline months from now without context, this is exactly the reason to stay subscribed to this channel. We will be covering the outcome of this Big Bang procedure the moment it is confirmed. So why does keeping these instruments alive even matter this much in the bigger picture? Because the questions raised by that 2018 crossing are still wide open, and the people best equipped to answer them are two aging spacecraft with a shrinking amount of power left to give. Why does the edge of the solar system sit at almost the same distance, no matter how active or calm the sun happens to be? What is actually causing particles to leak through that boundary in both directions at once? And does that leak rate change over time? As the sun itself moves through different regions of the galaxy? Is the overall shape of our entire solar system a long comet-like tail, stretching out behind us as we travel through space, or something closer to a sphere, or even something oddly shaped like a lemon, as a few competing models actually suggest? These are not small, trivial questions confined to academic papers. They are questions about the true shape and behavior of the invisible bubble that protects our entire solar system from the wider, harsher galaxy surrounding it. And there is no backup plan quietly waiting in the wings. There is no other spacecraft anywhere near that region of space right now. There will not be another one for decades, possibly much longer than that. Whatever Voyager 2 and Voyager 1 can still measure before their power finally runs out completely is, for the foreseeable future, all the direct data humanity is ever going to get from that part of the universe. There have been proposals over the years for a dedicated interstellar probe. A next-generation spacecraft built specifically to fly faster and farther than either Voyager, carrying instruments decades more advanced than anything available in the 1970s. But proposals are not missions. Missions need funding, years of design work, testing, and a launch window. And even the fastest realistic spacecraft using current technology would still take longer than a human lifetime to reach the same distance Voyager 2 has traveled. Which means that for now, and almost certainly for the rest of most of our lifetimes, these two aging machines are it. They are the only eyes and ears humanity has anywhere near the true edge of our solar system, and every single watt of power they lose brings that window a little closer to closing for good. Let's talk about everything else Voyager 2 has already given us, because honestly, the list is almost hard to believe. For a machine that was originally designed to last only 4 years, it is still the only spacecraft in history to have ever visited Uranus. During its flyby in January 1986, it discovered 10 previously unknown moons and 2 brand new rings circling the planet. It measured the planet's bizarre sideways tilt and detected a magnetic field so strangely offset from the planet's rotation that it still puzzles scientists studying exactly how planetary magnetic fields form in the first place. It is still the only spacecraft in history to have ever visited Neptune. During its 1989 flyby, the final planetary encounter of the entire Voyager mission, it discovered 6 new moons, including one large enough that many scientists believe it probably should have been spotted from Earth long before Voyager ever arrived to find it. It measured supersonic winds tearing across Neptune's surface, faster than anything recorded anywhere else in the solar system at that time. And it gave humanity its first ever close look at Triton, Neptune's largest moon, revealing active geysers shooting material miles into a thin atmosphere, and strong evidence suggesting Triton was not actually born there at all, but was instead captured from somewhere else in the outer solar system entirely. It discovered an additional moon at Jupiter that nobody had seen before. It gave scientists stunningly detailed views of Saturn's rings, revealing complexity that no telescope on Earth had ever been able to detect. It confirmed the active volcanic eruptions on Jupiter's moon Io, first spotted just months earlier by its twin spacecraft, and it captured the very first detailed images of the icy, cracked surface of Europa, images that hinted strongly at a hidden liquid ocean beneath the ice. And that would eventually help inspire an entirely new, dedicated mission built decades later, just to investigate that exact possibility further. Keep in mind, every single one of these discoveries came from instruments built with technology that would look ancient by today's standards, using onboard computers with a tiny fraction of the processing power found in a basic calculator watch. Nobody who worked on this mission in the 1970s could have guessed that these same instruments would still be returning usable science data. Nearly half a century later, from a region of space nobody had ever physically visited before, every flyby was a single shot. No second pass, no chance to turn around and look again if something was missed. And somehow, across 4 planets and dozens of moons, it kept working. All of that, from a spacecraft launched in 1977 before the internet existed, before personal computers were common, before cell phones, before GPS, a machine originally built to last just 4 years. Still working, still sending real data home, 49 years later and counting. And somewhere on board, riding along through every single one of those discoveries, is that golden record. A message chosen carefully by a small team of scientists and artists back in the 70s, containing greetings in dozens of human languages, music from cultures all across the planet, and recordings of ordinary sounds, wind, rain, a beating heart, meant to say something simple to whoever might one day find it. We were here. We tried to understand the universe around us, and we wanted you to know that we existed. That record was never meant to reach anyone anytime soon. It was meant to keep drifting long after everyone who built it is gone. And everyone watching this video right now is gone. Voyager 2 is not just a data collector anymore. It is a message in a bottle, still floating, still carrying that promise outward into the dark. If a video like this deserves to reach more people who have never even heard this story before, the simplest thing you can do is share it with someone. Not for me, but for a piece of history that genuinely deserves more attention than it gets. We are getting close to the end of this story now, but stick around, because the ending is the part that actually stays with you. If you have made it this far, you clearly care about the real story behind space exploration and not just the highlight reel version. So do me one small favor before we finish. Hit that subscribe button and turn on notifications, because the results of this test are coming very soon. And when they do, you will want to already understand exactly what you're looking at, instead of hearing about it secondhand with no context at all. Voyager 1 gets almost all of the public attention, the golden record, the headlines, the title of farthest human-made object ever built. But it was Voyager 2 that quietly filled in the exact picture its more famous twin physically could not complete on its own. It was Voyager 2 that carried the one working instrument that gave humanity its first true, direct look at what actually lies beyond our solar system. Not a guess, not a theoretical model, an actual physical measurement taken by a machine that traveled all the way there itself. Right now, at this exact moment, a signal from Voyager 2 is crawling across more than 13 billion miles of empty space. Traveling at the fastest speed anything in this universe is allowed to travel, and it still takes over 16 hours just to reach us here on Earth. It arrives faint, stretched thin by unimaginable distance, carrying information from a place that no other instrument currently owns is capable of reaching. And somewhere, inside a quiet control room on Earth, a small team of engineers is waiting on that exact signal, hoping that the riskiest procedure ever attempted on this spacecraft worked exactly as planned. No second attempt available, no backup hardware waiting nearby. Just one single chance, sent across a gap so vast that by the time we finally know the answer, the moment it actually happened will be in the past. Gone before we even realized it was happening. Think about how strange that really is. Every answer this mission gives us has already happened. By the time we hear about it, the spacecraft itself might already know whether it survived the Big Bang, might already be sitting quietly in its new setup, or might already be silent while we are still sitting here on Earth, waiting for a message that is still traveling toward us at the speed of light. We are always looking at the past when we look at Voyager 2, never the present. That is simply the price of reaching this far. And yet, it keeps going. Through the cold, through the dark, through decades nobody who built it originally expected it to survive, powered by a slowly fading heart of plutonium, wired together by engineers who are mostly retired now, kept alive by a handful of people, who learned a dying language just so they could keep listening to it speak. That is the real story of Voyager 2, not the quiet twin standing in a shadow, not the forgotten spacecraft nobody bothers to mention. This is the machine that saw what the other one physically could not, that is still teaching us new things about our own solar system nearly 50 years after it left home. And that right now, in this exact moment, somewhere between the stars, is fighting to survive just a little longer, so it can keep telling us the truth about the edge of everything we thought we knew. Somewhere out past the reach of everything familiar, a small metal spacecraft the size of a car is still moving, still listening, still speaking back. To a planet it left behind, before most of the people watching this video were even born. It never asked to become the most important instrument at the edge of our solar system. It simply kept working long after everyone expected it to stop. And maybe that is the real lesson hiding inside this entire story. Sometimes the quiet ones, the ones nobody is paying close attention to, end up carrying the truth the loud ones never could.